Hey, everybody, Jason here from Murideo. Thank you so much for joining us today. Today we've got a very interesting topic and one of my favorite guests of all time, Mr. Jeffrey Boccaccio of DPL Labs. How you doing, Jeffrey?
Hey, we're doing good here in Florida, aren't we?
We are doing well in Florida, and I'm sorry to say this for those of you who might be listening, but it is currently 73 degrees over here on the west coast of Florida and not a cloud in the sky. So sorry for the brag, but we got to do it.
It's a nice
How are you
place
guys
to
doing over there?
nice place
About the
to live.
same?
Yeah, it's beautiful here today. We're on the
Good.
East Coast, and it's beautiful here today. So
Cool, cool.
all I complain about now is it gets dark too early.
Yeah, it does. It's getting dark way too early. Definitely agree with that. So yeah, so thanks for coming to hang out. Gosh, this is probably our fourth or fifth podcast we've done together. If you guys haven't seen any of the previous ones, feel free to go back. I put them up on the Murideo YouTube channel. But we started off a really great episode. If you want to go back, starting the HDMI engine, which really covers, once you plug the cable in, what actually happens after that. So that was a really fun one if you want to go back and check it out. Before we get too deep into today's session, just want to let you guys know too, there is a question box over here in your control panel. So if you have any questions throughout the presentation, feel free, don't be shy. Just type your question in. I'm moderating the question box also, so if I don't get to it right away, we'll give you some time at the end and we'll go over those questions for you. So, Mr. Boccaccio, today we're going to be talking about AOC cables. What are they? Why do we need them? What makes them good? What we should be looking for when we're putting them in the system, and what can go wrong? I think that's about it, right?
That's enough.
Yeah, it's enough for today.
It's good. I mean, it was great to see these products come in because it was always questionable how they were ever going to make it work
Right.
because the interface has so many wires in it. And I have a small presentation, and the folks will be able to see what happens inside the connectors. I mean,
Hmm.
inside the cable itself,
Right.
because there's a lot of little monkey business that goes on, which is really okay. It keeps the integrity right on there. It does have its pitfalls.
Hmm.
So I do a thing on pros and cons of the interface with fiber, and but it gets us distances we could never do before.
Yeah.
And of course, now that as we move up, over 40 gigs, those are going to be very, very critical. And we started testing those. Started last January on some of the newer products that came in. And there's good ones and there's bad ones.
Sure.
It depends on how much the company wants to spend and do it right or do it wrong. But we do it with case studies. Everything we do here at DPL Laboratories is pretty much done by case studies. And what that means, and just so the audience knows, we do traditional high-speed digital testing. That's what we do here. And HDMI, along with any digital video, is basically the same thing. We test for the same thing. Maybe different amount of channels or maybe different configurations, but overall it's about the same thing.
Hmm.
And in HDMI, they really want it on the commercial side for consumer, and so there's a lot of them out there. And the, there's been issues with HDMI from the beginning. I'm sure everybody knows,
Hmm.
and we don't really want to go back there again. But it seems to have never stopped. It always seems to continue. And the reason why we even got into the testing business was because of the horrible horror stories we heard
Hmm.
back in the day, and we still get them today. And
Hmm.
all of those horror stories come in, and what we do basically is we listen to them, we find out what they're about, we emulate it here in the lab, we find out why it happened, what happened, and then we build a test process so that when a product comes in for testing, we can we can tell before it even gets in the street, if it's going to be a problem out there or not.
Hmm.
So the whole idea is case studies, excuse me. And we started off, we had about 40 or 50 case studies, and now we're at 203, I think, in
Busy
case
guy.
studies. Yeah. And we're gonna talk a couple about them today, in fact, because one of them, we have a few of them are AOC related, and they're done by case studies. So it's not like
Hmm.
you need to test it, and because what will happen is you'll get one of the integrators will call and they'll say, my AVR is not working with my projector, and I'm using an AOC, and I think it's a projector. I think it's the AVR. Immediately blames the AVR for that,
Hmm.
which is understandable. And reason why he did that is because he did a little troubleshooting and he jumped the AVR, went right to the source,
Hmm.
and this picture came out fine. And so that's a pretty good test, you know. Yeah, maybe it's the AVR that's the problem, but it wasn't the AVR. And when we finally emulated the whole thing, we found out the real reason why, and it wasn't a good discovery by any means. We'll talk about it today in the presentation. So that's what we're going to do today. We're going to kind of go through it on a hardware basis, just to quickly repatch it. We're going to tie it into HDMI copper. So for those of you who didn't have some of the background that we did earlier with Jason and the earlier shots with copper, we have a couple of slides there that just show you how the copper works. So you know, let me get that started, and that way there you guys can be tuned in on what happens with AOCs. And let me get that started, and I'm going to start it like this, and then I'm going to activate it with what? Okay, come on, guys. How do you
PowerPoint and it's all of its quirkiness.
Yeah, this should be giving me a. Oh, here we go from the beginning. Okay, here we go. So we're ready to rock. Okay, so DPL Laboratories, of course, I just gave you a little bit of summary on who we are. Been around a little over 10 years now, and now our new 48G reference standard is our standard now, with all of those case studies parked in. And what we have inside this system of test is a thing we have trademarked as it's called the argumentative matrix. And what it does, it takes all the case studies, and it also takes some of the traditional testing, and it basically argues those answers amongst all the case studies. And we've figured out what the values are. We have an algorithm that puts all of that all together, and we have a way of really determining what's going to be most successful out there in the field. And if a client comes in, which they do all the time, and they want to have them tested and they don't make it, well, then we help them get it back to where it should be. Or even clients that come in really good, they'll ask again, is there something better that we can do? And Jason, you know all about that.
Oh yeah.
So that's kind of what DPL Labs does, and it's all about the case studies. So today we're going to be talking about AOC cables, and more than just distance, and it really is. So basically, we're going to cover the pros and cons of AOCs, and let's just list those out. Here's a list of pros. They can go long distances, extremely low noise, and they're flexible. You know, that's all the good stuff about them. The cons are a little different. They consume power. HDMI is already struggling for power. It's been a nuisance since the beginning of day. They just didn't give us, in the specification, did not provide a good limit on that. Even though some rise to the occasion and build better power supplies, but the spec is low, and it's gotten us in trouble 100 times, 1,000 times. The other one is input sensitivity. This is something that people never even talked about. It's not even in the tests for HDMI or any other test. They never look at they don't look at the sensitivity levels. They look at what the overall transfer looks like, which is good, but we still have to think about sensitivity because we have source products that are putting some information out, and some of those are higher than others. You know, we've had some situations with Apple TVs where, you know, in a lot of cases their output is a little low, and if you don't have a good input sensitivity, you could be sitting there till you're blue in the face and it won't work. Yet a Roku may work, or, you know, some other source device. We'll go through that. Yes.
Real quick, just for the folks that are listening, I'm going to put into the handout section of the control panel a PDF file that kind of goes into a little bit about what we talk about with AOC cables and Apple TV. So I put that into the little chat box for you guys.
Perfect. Yeah, I wrote an article on this in CE Pro about I don't know, 5 months ago.
Yeah, it said August on it, I think, but
yeah. August. I mean, the response was just unbelievable. I didn't realize so many people were having trouble with it.
Oh boy, yeah.
And of course, there was a case study. You know, somebody came in and said, "Hey, I've got this AVR," and I read that. I said, "Oh, I said, let's look at it." So then what we do is we emulate it right here. We either have to get the equipment in, or the customer sends it in, and then we go and find out what happened to it. And we found it, and it was actually nobody's fault.
Yeah.
That's really bad, but it was really
Yeah.
nobody's fault. And we'll get through that. The next thing is severe DDC issues. Now, for those of you who maybe not know what DDC is the main channel in HDMI. Without DDC, nothing works.
Mhm.
You know, you can talk about having all the video integrity in the world, and you can even have power levels that are just great. But if you don't have DDC, you have nothing. And the reason is because DDC is the communication protocol intelligence for the system. It's it's how the both sinks and sources talk, and it's also where all the EDIN and HDCP and error correction and all the status control is controlled. So it's kind of like the brains that go on within the system. And this is why it's called an interface. It's an interface because it's grouping two entities together that have to talk to one another, and we have to look at everything about that. So DDC is a big one. And one of the last ones, which has been really unfortunate, is radiated emissions.
Mhm.
We always thought, I can remember, guys in the field. I mean, maybe when you too, Jason, where we figured fire was going to come in. Oh, emissions are going to go away. We never have to worry about emissions.
Yeah.
And it actually turns out that the AOCs are the worst.
Mm.
Worst. We send products into emissions every day, and the copper ones. I mean, we've had coppers that didn't make it, but we've had a lot of AOCs that just didn't cut it. And yeah,
In case people might not be familiar with why the emissions is such a big deal, could you maybe touch on that just a little bit?
yeah, sure. Under Ref 2.1, radiated emission is required, and it's under a particular section of radiated emissions. There used to be a Part 15 for many years. This is called CISPR 32, and it's primarily for multimedia applications, and it's so that we don't get any emissions from the transmission through the cable that goes out into the air and pollutes the air.
Mm-hmm.
It's dangerous because it can affect other processes. It could affect other things in the system. It could affect Wi-Fi's. It could affect cell phones. It can affect anything. Now that we're into almost a wireless type of society, so
Mm-hmm.
it's become a real issue, and it's required. However, many people aren't even doing it. We found out now that
Oh, not at all, even though it's
no,
part of the spec. Wow.
no, they're not even doing it. I mean, we have product come in. We have product come in that is stated it went through ATC testing, and they wanted to get the next test level, right, which is DPL, because DPL is like the ultimate in the test environment. And they bring it in, and we do all the testing here, and they did good. Some of them we found we caught them in some errors. DDC is one of them, but um, we sent it to emissions and it failed. And well, how did it fail? This has already passed once,
Mm-hmm.
and it failed. And when we opened it up, it was obvious. They had no shields.
None.
No,
Wow.
you have to have something. Now, even if you have something, it's got to be something good. I mean,
Yeah.
it's got to be, back in the days of cable TV, what do we do? RG6, right? And
Mm-hmm.
we try to get double and triple shields, right?
Right. Right.
Always, right? Well, this is just as bad, and it really produces a lot of problems. And what they didn't understand or didn't realize that in AOCs, we still have copper in there, and even though the copper doesn't run that data rate,
Mm-hmm.
the copper is like a perfect antenna for the input and output devices that are in the head shells of the AOCs. And that was another case study we did where we actually sniffed it. We ended up bringing in a sniffing tool that we could actually, sniff right around the
Yeah.
connectors, and we could see the emissions coming out of it. And it was like, holy cow! No wonder this thing is failing.
Sure.
And,
Sure.
and it wasn't necessarily much emissions out of the wire itself.
Mm-hmm.
Except for this one that didn't have any shield. But most of the ones that come in, they have pretty good shielding. But if they don't know what they're doing, when it leaves the head shell, it'll radiate. And if it
Mm-hmm.
radiates, it'll cause these problems. The feds don't like it. You don't want to get their bad list.
Yeah.
And the other side of it is you want to do justice to the system that you're putting in. And the
Mm-hmm.
last thing you want to do is have radiated emissions cause some other Murphy. We got enough Murphys. We got enough Murphys. I hear them all the time. So anyway, that's enough on that. Anything else, Jason, on radiant emissions?
No, that's perfect. I was just, making sure everybody just kind of understood the importance of that. That's all. Thank you.
All right, great. Just a little review here. This is what the interface looks like in easy terms, and I'll walk through it very quickly. This is under 2.0, so it's 18G, and it's 5 volts on the top. See, we have a 50 milliamp limit. That's not much. However, some sources may give us 100 mils or 300 mils. That's good. Right. It's really good. But, they don't have to. And so you get the lower ones. Apple, for instance, is low. They trickle between 50 and 100 mils. And sometimes if you try to put something on them like a AOC, AOCs can draw some current, and we'll get into that later. But anyway, it goes into the TV basically, and it basically does an about face and goes back into the source, and basically flags the source that, hey, I got a guy over here who wants to watch TV. And once that happens, it initiates status control, which is that pink DDC bar you see, and that's why the status control gets transferred. That's when HTCP comes in and all that kind of jazz. And then when all that's happy and everybody's nice and good, all these video lines begin to operate. And here we have 3 video lines, D0, 1, and 2, and of course we have a clock channel because in TMDS we still require a clock. Let's look at this a little differently. Let's look at it by wire. So same exact picture, except now we've broken it out by wires rather than by just channels. And if you notice, there's a lot more wires here. And the reason is because the DDC line requires 2. The Ethernet requires 1. Look what they're doing on Ethernet. So we have hot plug, Ethernet, and eARC all on wire. And that eARC is going to be something because you need some bandwidth with that thing. And if you're going to try to do it with wire, if you make 10 meters, you're doing good.
Yeah, right. Yeah.
A lot of people don't know that. And then you'll go down to D0, and now of course I'm doing 12 gigs here for 48, but same thing holds true in 18. There's 2 wires inside each one of these channels. So there's 2 wires in D0, 2 wires in D2, D1, all the way down. And D4 used to be our clock, and now it's a new video channel, and that's what gives us our 48. Now the reason why there's 2 wires there is because the system is done in full differential, and a lot of people don't know or understand much about differential, and we get asked this all the time, and so I put together a little slide thing for you so you can see how differential works. Because interesting enough, if I go to fiber now, let's go to fiber. Well, fiber is the same thing, isn't it? Except all the white bars, all the white ones are in fiber, and all the ones in colors are in copper. So we still have a good amount of copper in the hybrid AOC product line. Sure. And it doesn't matter who you go to, they're all the same way. They have to do it. And again, some are better than others. I mean, we've seen some that are absolutely stellar, and we've seen others that aren't worth, putting them in the garbage. So, it's that bad. But look at this next slide, because this will interest you. This is a fiber as far as what it looks like in real life. And notice it's single-ended. We don't have differential anymore. So you see, we don't have as many. There's only one D0. There's only one D1, D2, D3. There's only one. So they don't use differential in AOCs. And yet, first thing you'd say is, well, why not? Now if you know what differential does, which we're going to show you next, you'd say, I want differential back. But you really don't need it because it's fiber. It already takes care of a lot of the differential conclusions that comes up by using differential signaling. So let's look at this in this that's the instance circle around the ones that we want to look at. So what is differential signaling? How does that work, and what does it mean? And basically, we take like D1 and we split it into 2, and then we take it and we say, okay, we're going to call one of these plus. Notice the D1 on top is a plus, and the one on the bottom is a minus. So we have a polarized area now. So we have a D1 plus and a D1 minus. Now we take data. So here's some TMDS data that we're going to bring in, and this TMDS data is just square waves like anything else. But you can see this is done in single-ended. This is done in and basically one cable, one wire is needed to do that. However, within the source, the processor in the source takes that and moves it into differential, and it changes it, and it does this to it. It brings it in and splits the phase.
Mm-hmm.
So you can see that the positive one goes positive and the negative one goes negative. Now, if you tried to use this, it would never work because the positive would cancel out the negative.
Right.
All right. So that's how we induce it. That's how we get it to go. Then a little trick here. If these are out of phase by 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 on purpose, they're out of phase by purpose because now if we look at it, we say, well, what about the noise level that's on those wires? Well, the noise level isn't from the source, right? The noise level is either from radiated emissions, some sort of interference.
Mm-hmm.
It's just noise in the line. And so the signal really doesn't have anything to do with the noise in the line. The noise in the line was always there. So what they do is they basically take the bottom channel and notice that these are in phase. So everything noise is in phase. Everything that's signal is out of phase. So what do? Well, that's pretty simple. You just take it and you flip it around. So we basically invert the bottom channel.
Mm-hmm.
So now both signal channels are in phase, so they work together with each other. But then, you got this little situation here where the noise is out of phase. And when you put those together, well, guess what happens?
Boom.
The noise goes away.
Right.
And now we have a nice clean signal. So that's kind of how differential works. But because one great thing about differential signaling is its noise immunity. It has a teeny bit more gain, but the big deal is the noise immunity. And since fiber has none, fiber basically takes the differential and makes it single-ended inside the input connector. So there's electronics that do that. They convert it into single-ended, and then they fire up the VCSELs. And the VCSELs are the LED senders that transmit down each wire. So you need four VCSELs in order to do 4 channels, and that's how that works. So, but what a lot of people don't understand is that fiber also is a great insulator, isn't it? You can't run any direct current on that thing. I mean, it's fiber. I mean, it's plastic, right?
Yeah.
And so the interface though doesn't work that way. It was never designed that way, and it's still not designed that way. And so now fiber companies have to kind of like make it work somehow. And I'll show you what I mean. You see on the left-hand side, we've got an HDMI source, and that's where all the video and the control and the audio comes from. And of course, the other side is the output side. No big shakes here. However, what they do is on the sync side, on the display side, there's actually power there. There's a little bit of power in the sync. And they use that power to actually send a power thing or power line back to the source. So if you look at the source, you see those 2 switches that are hanging there on ground? They're open right now.
Right.
Well, when you take a DC source and you send it over there like this, well, now that DC is going to go to the switches. When the switches are open, it's a high. When the switches are closed, it's a low. So they don't use switches, they use FETs. But they have to move very quickly. And they have to go high, low, high, low, high, low, high, low. So you've got to have that 3.3 volt source, which they have recommended, that goes backwards on the wire.
Mm-hmm.
Well, we can't do that with fiber. In fiber, we basically insulate.
Mm-hmm.
So we don't have any more DC coming in. And this has been a problem. This is one of the case studies because this, and I got to give the fiber guys a lot of credit in the at least in the silicon side. And that's this. See, they have this 5 volt line going through. We talked about earlier. Well, what they do is they say, hey, look, if the 5 volt line is going through the source, the input side, why don't we just pull some voltage off that, and we'll use that to emulate the 3.3 on the switches. Works great. Great idea. Then we still have the 3.3 volts flowing down at the display. So what they did there is they said, okay, well, let's not lose that one. So they inserted a little thing called power harvesting.
Mm-hmm.
What that is supplemental power that they use to power up the receiving side of the AOC. So the AOC is drawing current to run its electronics, but it's actually drawing more current than you think because it's actually pulling some current out of the display also. This is where we get into trouble because that spec going into that spec that goes from the sink back to the source is a spec, there's a number there. And actually they gave us a number and we don't even use it anymore. And the reason why we don't use it anymore is because of case studies.
Mm-hmm.
We found out that, well, what do? You have to make sure that the emulated supply voltage is really emulating the right number. So anytime now an AOC comes in, when it goes into our system, it automatically gets read as far as how much voltage it's supplying. It's got to be at least 3.2 for us to be happy.
Mm-hmm.
But they could be as low as, we've seen them come in as low as 2.6. And you get down to the 2.5, 2.6, 2.7 range, and your AVR or your cable box or your Apple TV, it's thinking it's going to see, 3 to 3.3. And and these clowns that build these things, I tell you, getting these products in and seeing what they built, you wonder if they even tried the damn thing. It's just unbelievable. And so, again, that's what we try to do. We try to watch and make sure, okay, yeah, maybe it'll work at 2.8, but no, we want it to get to 3.2.
Mm-hmm.
2, you'll pass, and 3.2, you'll never have a trouble in the field. And then on the other side of the scale, we want to make sure that it's drawing the right amount of current because we only have 50 milliamps, right?
Right.
So the current is important. In most cases, we've seen them as low. I'm talking about current day. We've got a couple here that are operating as low as 30 mils.
Okay. And
Now
there's
that's,
with the 50 mil, I think there's only like a 5 or 10% tolerance, right?
yeah. You got very high tolerances on that.
Yeah.
And but at 30 mils, you're doing pretty good, I'd say. But that's like 1 or 2 that are doing that. Now there's
Yeah.
downsides to that. When you start lowering the current, you also lower, some of the poop you get out of the electronics. So they
Mm-hmm.
have to have a balance in there, and how much EQ, what kind of gain, maybe an increasing gauge. Well, there's all kinds of things you may want to add, but there are some downsides to it. But if you watch your P's and Q's, and you can get down to 30 mils, it's a good deal because you wouldn't need any external power.
Right.
Now, I'm sure most of the folks out there are saying, I never use external power.
Mm-hmm.
You're crazy if you don't,
Mm-hmm.
because we don't know who's doing what and how
Sure.
much current is being available. So what we try to do here is we try to influence the DPL members that have AOCs to use some form of external power, and at least supply it in the box.
Right.
Because if the installer gets out in the field and it doesn't work and he doesn't know what to do, well, it's pretty easy to try sticking the power in and see what happens, right?
Sure. Yeah.
And it could save your butt, and you could go home and get paid. And that's the key, right? So the current thing is bad. We've seen them as high as 150 mils.
That sounds scary. Like you're gonna zap something.
That's almost as much as that's almost enough current to produce heat.
Right. Yeah.
I
Right.
mean, it's like mind-boggling that they do some of the things that we see, and it's it's disappointing, especially now we're over 10 years into it. You think they'd learn, so it doesn't work that way.
Is that enough to damage like an HDMI connector on a product?
No.
No.
You mean the high current?
Yeah.
Oh, no.
No,
I
it's
mean,
not enough.
you run
So
half.
that's good at least.
Yeah. Well, we're gonna have, they're now offering a new thing. Next year we should see high current
Yeah.
come in from HDMI,
Right.
and I'm not even gonna tell you what they're gonna do, because I know when I tell you, you'll just get upset. A very easy.
We'll save that for next time.
Yeah, we'll save it for next time. But how they're doing this is just. So anyway, let's get on with it. So what are the pros and cons of input sensitivity? We talked about this earlier, and what that means is that you see on the left we've got our little square wave here, and it's railing out probably at rail, typically between 500 and 650 millivolts of rail signal come out of the source. And then it goes through the HDMI cable and it produces that output. That's an I pattern. And that's a very nice, clean output. Right?
Yeah,
Very,
that's
very
good.
attractive, right? But let's see what happens. Oh, and this is the case study, right? This is when the Apple TV thing came up. Let's lower that input a little bit.
Mm-hmm.
And when we did, we found that the particular cable that we were testing went into the dirt.
Mm-hmm.
And we didn't go that low. We went, I think we went down to, I don't know, I think about 280 mils. I mean, but if you want to go to the basement, in other words, when you go to the really bottom of the spec, they don't want you to use, the televisions won't accept anything less than 100 mils.
Sure.
That's their Mac. That's all they'll take.
Yeah.
So, well, okay, but you think that a source is going to be full rail. I mean, it's right from the source, right? But we do have cables. We have copper, and the
Mm-hmm.
copper has to transmit down. It's going to lose some gain. So, yeah, I can see all that. But in AOC, I got a problem with that because AOCs, remember, are working on pull-ups. They're working on voltages that are always going to try to make them rail. So once you get an AOC activated, it pretty much goes to rail, just like the one that we just saw earlier. I'll go back to that. It goes back to rail like this. So you see, this is back at rail now. I mean, and you can see how good that eye pattern looks. But really, whether it's 500, 600, 400, or 300, it should produce rail. That's how it works. So anyway, this one here did not do that. Then we have others that come in that are absolutely amazing. Here's one. Look at this one here. That's low sensitivity. Here's the next one. Look at that.
Ooh, that's low. Yeah, but then it's still a nice diagram, eye pattern.
98 mils. Can you imagine that?
So that should be way too low, you'd think.
Yeah, but the AOC picked it right up.
Right.
Picked it right up, reproduced it, and the installer would never know
Right.
that the source was only putting out a little bit. And that's what everybody should do. Everybody should overbuild.
Yeah.
If everybody just overbuilt, we wouldn't have all these issues. You got so many people in the sandbox that are throwing sand at each other, and that's what they do. It's all a big blame game.
Yeah.
He did. They blame. It's politics too. But you can see that difference is so dynamic.
Yeah.
And I remember I was so shocked and stunned when I saw it. I had to go back and try it again. I just couldn't believe it. It was just incredible. Now there's a downside to that also, and that is that it's more easier to saturate.
Mm-hmm.
So now if you give it too much, it may saturate.
Mm-hmm.
So as good as this was, what they really should have done is made it so that it worked with about 150 200, which is you're always going to at least get that, and that would give in case something came in that was huge, it wouldn't oversaturate, and then cause saturation problems in the eye. So that's what that's about. So that's high sensitivity. Okay, case studies. Another one I2C. Let's just run. We did this before, but I'm going to do it again.
Yeah, sure.
If you look at this transmission line again, under 2.1, you've got this DDC line, which is what we're going to talk about. And this DDC line is vulnerable. It's vulnerable because it carries EDID.
Mm-hmm.
It also carries HDCP. And of course, in the middle, during some timing, it also covers status control.
Mm-hmm.
Status control just came in 2.0, and they added a bunch of crap in status control. I mean, they had error correction and all kinds of stuff. It's a litany list on that.
Sure.
But it just loaded up the bus with just more data to transfer. So it's a very important data, and it's got to be kept in very good integrity. So it does video scrambling changes are done in this, HTC of course, error correction, reference clock conversion because you have to have that for 2.1, and of course the assignments for the new wires have to be done. That's all done under I2C. And so if that doesn't do its job right, you're in big poo-poo.
Yeah.
And we don't want to get you there. So an I2C interface, which is what this is, they call it DDC, but they borrowed it from Philips.
Yeah. Oh yeah.
It's called an I2C, and
Right.
and we're talking way back in the early 70s, so it's not exactly new. But it's very reliable, does a very good job, and the way it works is like this. It's basically we've got a source. Here's your DDC I2C source, and then over on the other side we're going to have a sink that is I2C sink, and then we have wire that connects the two. So what happens is, let's say we go 2 meters. Well, there's a certain amount of capacitance in the wire at 2 meters, and we can measure its rise time. That's what that little picture is. And the rise time here is 0.33 microseconds. And that's extremely good. That's 330 seconds. So that's an extremely sharp curve. And that's what we like to see. Okay, here's 3 meters. So we go up a little bit, 433 nanos, 0.33 micros. Again, extremely good. And then we get out to a little bit more, 5 meters, and now we're going up to 600 nanos, or 60 micro, 0.6 micros. 7 meters, it climbs more, 783. And this is on a particular cable. They vary depending on gauge. So you have to be careful.
Sure.
And then this particular cable, by the time we got it to 10 meters, it was out to over the mark. Now, Philips has a requirement, you can't be more than 1 microsecond. So it's failed. Now, it turns out that HDMI didn't really follow that. And they didn't follow, and you kind of have to reverse engineer it to figure it out. And that is that they don't give you rise times on their tests. They just check for capacitive loading. Well, it doesn't tell you anything. You don't see the actual data. So if there's an overshooting, or if there's noise in the line, or if there's ripple from the supply line, you don't see any of that with that measurement. Whereas with rise time measurements, you see everything.
Yeah.
And that's what we show you there, right? So what happens is, and let's just take this 10 meter now and just look at it a little closer. And we're going to blow it up so we can see that picture. And you can see here that right here is where you can see it says delta T. That's the change of T. So that's 1.05. It's breached, right? And it's got a very big arc to it. That's why it's breached. And because it breaches that much, it's highly likely that it'll go bad. But what we did is we reversed engineered it and said, okay, how much capacitive loading would cause X? Well, HDMI says that you can have up to 700 picofarads on their copper. 700. Philips doesn't say that. They say 400. So if we actually took the 700, interpolated it backwards, the rise time actually can go up as high as 1800.
Oh, wow.
Yeah, we just discovered that in the last few months because of AOCs. We're always holding standards straight Philips. And then nobody was passing. And we said, wait, we got to do something about this, And then finally I said, maybe we should break away from Philips here and see what the hell HDMI is up to. And it was surprisingly, because right in the spec they say follow Philips specifications, and it clearly isn't. But it makes it so that we have a little bit more leeway, and more cable companies can now get through that. And if they don't, especially when you get over 20, 30 meters, you have to go into some sort of support. And there are devices you can put inside the AOCs that do that. But then again, if they're made wrong, and not wrong, I'm sorry, I take it back. If you don't watch how you're doing them, you can overdo it. They'll overshoot a lot if you give it too much correction. And so we see them come in and they're really good. We see them come in at 80 meters, and these things look like they're 3 meters long. I mean, absolutely fantastic, except they got a real bad overshoot problem. And the overshoot causes it to hiccup, and the hiccup causes the DDC line to go down.
Right.
So that's what that's about. So the whole idea on HDMI is climbing that mountain every day. And we do it here in the lab. It's a lot of fun. It's always great to see new products coming in. It's always good to hear from the guys out in the field. And you're more than welcome to call us anytime or write to us. And we're always looking for case studies. We got a ton of them, and we've got the only ones in the world. We have the only setup of case studies that has followed and tracked everything that all you guys have been through throughout the beginning of time.
For you guys too. Sorry, I didn't mean to interrupt you there. I just wanted to let everybody know. I'm going to put into the chat the DPL website, so you guys can go check it out. All the contact information will be there too.
We're right in the middle of upgrading that right now. So it's to take out a new look, and of course that's where all the new numbers will be. So the current website's okay, but we have a new one coming now that is it's going to be great because it's going to have a lot of resources there. It'll have a lot of help for everybody in the field. We have lots of data that we've recovered and gained and learned over the last 10 years. Anyway, that's my show today. So I never figured I can kill it. Okay, great. So we're back to this, and I should say, okay, we're back.
A question came in, and this is really funny because we talk so much about video. When we look at those TMDS lines or the FRL lines, where's the audio? It's a good question. It's a very valid question. When we talk about video so much.
Yeah, the audio is embedded in the video.
Yeah.
I mean, when you think about it, audio is nothing. I mean, when compared to what we're trying to do.
Oh, it's tiny, right?
What's great about this is you can dovetail a lot of the stuff into each wire, and you can add different forms of modulation. There are tricks to that. You have to make sure you do that right. But I can remember, in school we did some multiple modulation schemes over the same wire, and I couldn't believe it could actually work. And you broke them out. You broke it out at the end, and that's what HDMI does. They break it out into audio.
Yeah.
When it gets into the receiver chip.
Good. Let me see if there's any other.
This eARC is going to be an issue. I'm telling you.
Well, it's funny because we teach in our classes to the installers that the eARC is it's so much more bandwidth, and it doesn't rely on CEC and all these other things, and everybody's going, oh great, this is awesome. But what kind of problems are you sort of anticipating or seeing?
Well, so far the only problem we've had is when someone's trying to run eARC over the Ethernet line, and it doesn't have the bandwidth. And I can tell you right now, if the guys in the field had an old cable way back in say 1.2, and you broke it open and you look at the gauge of the hot plug, it was really, really teeny. It was about the same size as the voltage gauge, very, very teeny. But if you looked at the video gauges, they're always a step up because they have to handle the bandwidth, right? And then there was one other wire in there that they never used, and it goes to pin 14. And they just figured one day maybe they'd use that wire. Well, then one day came, they want to put Ethernet in there. Well, for Ethernet, it's differential, remember, just like we talked about earlier. So we need a plus and a minus. So we have hot plug. Hot plugs are minus. Pin 14 is our plus. What they do is now they ride Ethernet on top of the DC in the hot plug. It's perfectly okay. You can do that. You can ride it right on top of it. Not a problem. But here's the issue. If you try to do that on a 1.2 cable, the gauge of the hot plug and even the wire on pin 14 is real teeny, and it won't handle the bandwidth. So you'll see everything after like 1.4 when they brought Ethernet in. You'll see that the two wires that are used for that, which now have to be shielded, by the way, right? Just like a regular TMDS line, they have to be shielded, but they're the same gauge as the video. So you look at it like a 24 gauge, which is a monster, right?
Right.
And before you'd open it up and it was just these two little wires.
Yeah.
Now you open it up and that Ethernet is as big as the video gauges.
Yeah, that's good.
So, but again, you're not going to get far with it because look at the size of the AOCs. They're very teeny. When you look at the size of the cable, it's so teeny. They're flexible.
I've got it.
Wonderful. But I see some electronics in the future to fix that.
I've got one here.
Oh yeah.
I've got one here for people to kind of see. Because you were talking about before, I mean, something has to convert the electrons and the photons and then back on the other end, which I'm sure you could talk about this for days, but we really stress the importance of, making sure you have the orientation right. So like when it says source on the head shell, make sure that goes into the source. But if you guys want to kind of take a peek at that, camera focus in. I mean, look at how much is going on there that we never had to worry about with regular, with regular H. There's a little chip in there. There's some protective coating, it looks like, over the lines that are coming in. They're all soldered to that tiny little board.
And they're glued.
Oh, it's okay. So it's a glue, yeah.
And those traces, those little teeny traces from the wire to the connector, because from the connector wire, that's where all the emissions is coming from.
Right. So there's like there's not a lot of or any sometimes shielding on those colored wires that are coming in, which are the
Yeah.
data lines.
So
Yeah,
they have to do a really good job in the head shell to make
yeah,
sure it's double shielded, and then they've got to make sure that when the wire exits the head shell,
right.
it doesn't leak out. And
Yeah.
there's methods of doing that right,
Hmm.
and they're proven methods. But I can tell you, there's a lot of people are not following this, and until they get caught, they're going to continue doing this, and you're best off just getting something that has the radiated emissions standards, which is again CISPR 32. And
Hmm.
don't have somebody say to you, well, I went to Europe and had it done by some other standard,
Yeah.
or oh, by the way, it's part 15. It's okay. No, it's not. It's not. It's got to be done this way.
I know we get calls a lot of times, and when we're doing our classes, somebody will always chime in when we talk about AOC cables, and they'll say, "Man, I've used these in the past, and they work. They work fine. These nice long distances, and it's uncompressed, unlike other technologies go long distances, which is great for the video files and nice TVs and nice projectors. But man, the ends get hot. Is that okay? Am I going to burn the house down?" And in a lot of cases, we say, look, guys, they're going to kick off a lot of heat. There's a chip in there. There's electronics going on, and we've never dealt with that before. So when somebody's been installing regular copper cables for all these years, they never got warm or anything
Yeah.
like that to the touch. So people are calling in now who are using those AOC cables for the first time, and they're like, man, are these things supposed to be getting warm like this?
Now, when they start pulling 130 mils, they will.
Yeah,
And
right.
again, they're getting much better today. And plus, you get down into the 40 to 70 area, and
Hmm.
that's a good area. You can
Yeah,
use supplemental power if you need to, and a lot of the companies are at least giving you 100, 150 mils coming out. But the
sure.
problem is, it's kind of like the old problem we talked about so many times, and that was plug and pray.
Yeah, yeah,
And that's what happens. That the integrator now goes out there and okay, it's all installed, they've rewired it, they did other stuff, and now I'm going to plug it in and let's hope to God it works.
right.
And it's just one of those things we talked about today. And that was only what, 3, 4?
Yeah. Hmm.
We got tons of them that
Yeah.
go on, so
Yeah.
um,
Um,
fun.
do
It's
you,
fun.
do you think people should take, because there are electronics and a lot going on in here, um, I do encourage people to maybe handle these, at least the head ends, try to handle these with a little more care than you would on a regular cable. I mean, there is some wire relief and some strain relief here, but not like a copper cable. So in other words, you drop something like this on a tile floor and the head shell explodes, and now you've exposed the electronics and things like that. But if the head shell stays intact, there might still be some disconnections in here and broken solders, and maybe there's physical damage. Maybe the chip in there just took a hard hit. But would that be fair just to tell people like, hey, handle the ends at least with a little more care?
Yeah, I don't think agitating the end as much as I mean like dropping it or something like that. I don't know if I mean, yeah, the strain release on these are nowhere near as good as copper. I mean,
Right, right.
small fibers that are coming out. When when you break it apart like you did, Jason, you
Yeah.
can see fibers coming out and the strain relief, and then they go into these plastic chutes,
Hmm.
um, and they're basically inserted and glued, and you yank on it hard enough,
Hmm.
you could do something there,
Sure.
because how many times have you done that? And you see one wire creep back further than the other.
Yeah. Oh yeah. Yeah,
Same
for
with that with
sure.
fiber, and it's a great it's great. I'm not saying it's bad. I'm advocating. I'm saying it's great.
Hmm.
Just make sure you get them that don't put you in harm's way.
Yeah.
Again, if they're DPL listed, you don't have to worry about it. We covered every single aspect of what they will fall into.
Yeah. I wanted to show you guys this too because we touched on it just a little bit ago, but the 4 lines, instead of having a positive and a negative for each line, you've just got these 4, and because they're fiber, they're super thin. They do have a coating on them, of course, for protection, but people look at these and they go, how can that wire be any good? Because it's only my camera would focus right, but you get the point. It's so thin. How could that wire possibly be that
Yeah,
good? And it's because those fibers are, correct me if I'm wrong here, and I guess it's probably depending on the manufacturer too, but I've seen some specs where they, they'll advertise, marketing people will say, oh, it's thinner than a human hair. So it
I don't
just
know.
doesn't have to be that big.
Yeah, I don't think they're that big, but
Yeah.
that size. But yeah, they're
Um,
very small. They're very small.
this is a great question for the installers out there. What's this stuff right here? The Kevlar.
That's filler, right?
Yeah.
And you
It
know what
helps
that
you. Well, you can pull the cable, and the Kevlar keeps the strength,
it
right?
does. It does. It also keeps it supple.
Yeah.
So when you bend it and turn it, the wires inside can slip
Right.
inside the
Right.
jacket. So that's an art. That's an art. There's a skill to that.
Oh, sure. Sure.
It's the same thing in wire too, by the way, in regular
Mhm.
copper. There's a skill on how those wires are placed
Right.
inside. They don't just lay them in there, they've got to
Right.
be, and especially if they're bent and turned around and all that,
Mhm.
they've got to be uniformed because we're dealing with such high data rates.
Yeah.
Yeah.
The other thing that's nice too with these is shameless plug. We'll talk about the bullet train cables, but if you run this cable and 5 years down the road you need more bandwidth, you can strip the fiber, you can strip the jacket back, and you can re-terminate that piece of fiber with like an LC or an SC connector, and now you've got a fiber transmitter and receiver on either end, and you don't have to pull a new cable. So that's super helpful for future use.
It's extremely helpful. Again, it'll require skill and tooling, but if the right tooling is available, I mean,
Right.
we've seen it at the shows, Jason.
Oh yeah, you can.
They're good.
We partner with Clearline specifically.
Yeah,
I'm
yeah,
sure
yeah,
there's
yeah,
others, but we partner with Clearline, and they make this nice little kit
yeah.
that'll let you re-terminate that fiber. And then if we look at the fiber, of course, that's all your data, and then all you have for the rest of it are just these little guys right here. And this
Yep.
is like DEC and the other things we talked about.
Mhm. And there should be some
And
shield.
yeah, there's going to be some shielding right here.
Hmm.
And guys, this is it for copper. So when you have these tiny little fiber lines and not a whole heck of a lot of copper in here, you have some Kevlar to keep it nice and strong. You end up with a cable that's much easier to pull. It's a lot thinner seeming,
Now
but there's a lot going on in there.
on that particular cable you're looking at there, what's inside the shield? Are there two wires in the shield?
Yes, there's a twisted pair that's shielded.
Ah, okay. That's
I was
the
trying to peel it back, but I'm having a hard time.
yeah, that's the DDC wires.
Yeah, of course. Yeah, of course, of
Yeah.
course. And then uh, you've got your, ooh, I can stand straight. You've got your DDC line right here, positive and negative, and then that's ground, right? And then there's a really, really thin one. What's that for?
I can't see it.
Yeah, it's hard on camera, but it's much, much thinner than the two coppers.
Okay, so is it but it's got an insulation on it?
Just a little bit.
Oh, it's got insulation on it. Okay.
Yeah, just a
That
little
would
bit,
be
not a
odd. I
ton.
wonder what they use that for, unless it's some kind of drain.
Yeah, it could be. It could be a drain wire, but super, super thin. But this is what's nice. I mean, if we talk about the biggest benefits of the AOCs, and I'm seeing with Bullet Train at least, we're up to 100 meters now. So do you anticipate that if a cable is constructed well enough that we might see more than that one day lengthwise?
I do.
If you had to predict and if you had to
I do.
guess.
I do. But you're seeing, we're seeing a little changeover now as people are coming with 100% fiber rather than hybrid.
Oh, cool.
And I mean, it's good. I mean, the problem is you need two power supplies
Right.
because now we have no way of getting power down there.
Um, when we start dealing with HDMI cable power, maybe next year, maybe the year after, whenever, how will that change the game a little bit, or will it?
Well, by that time we move to extra power. I don't know. You see, the problem is going to be the sink side.
Right.
No way of
Right.
getting power to the sink, so you have to take that module down there and power it up somewhere. Now they could probably
Yeah.
power from a USB, off the off the TV. That's fine.
Hmm.
But when when they come in here like that, it's like I got to change the jig, because
Yeah.
we have these fixture jigs that are used, and I said, no, okay, well we got to change the jig for this one.
Yeah, sure.
It's I don't know. Maybe the integrators think the same way when they're installing those. I don't know, but
The other thing with HDMI cable power is both, let's say you have just a simple setup where you have a source and a TV or something. For HDMI cable power to really work the way it's supposed to work, both of those things have to actually support it. So it's not just going to be some universal plug and play thing for everything all the time.
yeah. You mean both source and sink would have to support it? So
Right. Yeah.
yeah, I mean, again, if somebody were to make if somebody, let's say some AVR company decided to do a 1 amp supply,
Hmm.
the display probably wouldn't even know it.
Yeah, if it was
It's
that low.
operating just low current anyway. It's basically, we call it source current. It's source current. So okay, it's there if you need it,
Hmm.
and if you don't need it, fine. It's still going to be there, but I don't believe it's going to hurt anything. Now maybe in the newer chipsets we haven't seen yet, but I don't know. I doubt it. It's more work, more money. They don't want to spend any more money on this. They
Oh,
want to
of course.
spend sets, right?
I'll share my screen for just a moment here so people can get kind of a little bit of a sneak peek, if you will, at some of the power adapters that come with some of the cables. Give me just a moment here. Okay, and then we're going to show my screen. And then Jeffrey, tell me, can you see my screen right now?
Yep, I sure can.
Okay, so what we're going to look at here is this guy right here. So for those who may have not seen this before, we've got this power adapter that's helping out in this case, it's the back of a television. So we've got the HDMI cable plugged into this little dongle, if you will, and then that's actually plugged into the TV. And then there's a wire coming off of that. We need to get power more than just plugging it in. Here, we've got to get power to it. So it plugs in either to the USB port on the TV, or if you really needed to, you could plug it in like a wall wart, right? Like what you use for a cell phone charger.
Yep.
Something we've been warned about, and we've even seen before, is this setup doesn't always work plugged in for power over USB on the TV in this case, because maybe the TV's USB port doesn't supply enough power for this to work right.
Yes, I heard the same thing.
Yeah. So
yeah. I mean, I think the newer TVs are now going more toward USB 3 and 4.
yeah,
Which
that'll help.
tends to have more current. But
Sure.
but one of the things about those connectors is that, okay, yes, they put power into it, but you have to remember, like you're saying, they put that on the output stage into the display.
Right.
So that means that the output of the AOC now that we saw earlier, that slide, now has to travel through that connector.
Mm-hmm.
Right? So you've got a connect and a disconnect. So once you do that, we have discontinuities with impedance, and then it goes through a board, and that board's got losses,
Mm-hmm.
and then it gets connected and disconnected again.
Mm-hmm.
So not only is it's not that easy to make those. It's very hard to make sure that they have the integrity to handle the video, especially when you get up over 40 gigs.
Mm-hmm.
And that it does. So you're doing really well with that.
We sometimes will recommend on the longer lengths something to try. It doesn't always help, it doesn't always work, but sometimes we'll tell people, what happens if you power both ends? Maybe this is a really long cable and you use one of these dongles on the source end, and you go through an 80, 100 meter cable, and then boom, you can power it on this end as well. What do you think about that?
Well, you can do it. I mean, I'll tell you why. Especially
we tell people to try. For
when you
part of the troubleshooting, let's just try it.
When you go 100 meters, there's so much resistance in the line that it's almost acts like a buffer between the two. Now,
Yeah.
granted, it's great to be able to have both there, so they're they're powering both sides. But in some cases, you got to be careful because should something go wrong, see, you have to think about Murphy's law.
Sure.
Say that one power supply, one wall wart fails, but it didn't go dead. Instead, it lost its regulation and went up.
Mm-hmm.
Well, now it's gonna go backwards, and it's gonna start backfeeding everything high.
Right.
So you got to those things you have to watch. So if two were being used on both ends like this,
Mm-hmm.
and one of them had a little bit of a problem, one may backfeed the other one, and then
Right.
that could happen. But again, I'm really pulling straws in this one because, at 100 meters, there's so much resistance in that line.
Right.
They wouldn't even see each other. I mean, it would be. I don't think it'd even be worth talking about.
Yeah. Good. Let's see if there are any other questions, because we're right on time here, which is awesome because we can very easily run over time on these conversations. But it doesn't look like there's any more questions. So, just to do a quick little recap. What are some positives? What are some negatives? We can go extra long distances. We no longer have to worry about, power issues in the environment because it's fiber. And we're completely uncompressed. So
What's also really good about fiber, and I mentioned this earlier, Jason,
mm-hmm.
and actually it almost holds true for almost anything that's active.
Yeah.
And that is that when it's powered up with an outside supply,
Right.
remember it's always reconstituted. So the rail is reconstituted.
Mm-hmm.
And so you're almost guaranteed that you're going to get a good signal on the end of the unit. I mean, it's almost guaranteed, unless you've got a DDC problem, which has nothing to do with the signal.
Right.
The only thing that's going to disturb the signal really is if the input sensitivity is wrong.
Right.
As we learned, right? And that's been a good one. I mean, we've had, I don't know, probably 20% of the cables that came in so far have not made that through.
Yeah.
And you don't want to be out there with them. You don't want to be out there with those things.
Right. Good. Okay, cool. I don't have anything else for you. It doesn't look like there's any more questions in the question box. Thank you guys so much for hanging out. The session has been recorded, so if you have any friends or colleagues who couldn't make the live session, I'll throw it up on YouTube here the next couple of days. I'll try to get it up before the weekend, and feel free, pass it around. I did put that Apple TV AOC article that Jeffrey wrote into the chat box, so guys, feel free to take a read. It's a really simple read. It's one page. It's not like a 50-page white paper or something like that, but it's a quick read. It helps people understand a lot what might be going on with these Apple TVs when they're paired up with AOC cables. I also put the DPL Labs website in the chat box. And as Jeffrey said, as busy as he is, he's happy to take all of our questions, whether it's me or you guys or whatnot. So yeah, go ahead.
We gain tremendous knowledge. Just tell us what's going on the field.
Yeah,
we can help you.
Absolutely.
It's good. I'll tell you that next month's CE Pro, I'm not going to tell you what it's about, but I'll tell you that today we talked about AOCs, right?
Mm-hmm.
Next month's CE Pro, we'll talk about can there ever be a cable too good?
Oh, too good of a cable.
Oh yeah, great. It's a great article. You should read it.
Those are the really expensive ones. Well, cool. Thank you guys so much. If you have any other questions that maybe you didn't think of during the session, feel free. Jason@murideo.com, and then Jeffrey, what's your email?
Yeah, Jeff@DPLLabs.com.
Cool. Super simple. Thank you so much for hanging out, and it's always fun.
Take care of yourself, okay?
Thank you, sir.
And
we'll talk soon.
Talk to you, Merry Christmas.
Oh yeah, you too, man. Absolutely. I will be enjoying the Florida Christmas. There has been many times, last year being one of them especially, that we've gone to the beach on Christmas Day. It's kind of nice. We're very privileged in that way.
Great.
Yeah.
Did you see that? Did you see our Thanksgiving card sent to you? Did you get?
I did. Yes, thank you. I did.
Good.
I did. Very cool.
Little fun there,
Yeah, for sure, man. That's what it's all about. Let's have some fun. Let's plug some stuff in. Let's hope it works. And if it doesn't, let's fix it and let's help the industry get stronger and better. And we'll keep chugging along here, man. It keeps us busy and it keeps us employed. How about that?
You bet. Okay.
Cool. Thanks again. We'll talk soon.
See you.
Bye.
Bye-bye.